All right, lecture 4, the basics of thermodynamics. In the last couple of times, we've been talking about some of the most basic ideas in thermodynamics, or that lead to thermodynamics, especially the idea that what we observe experimentally in the way systems behave can be controlled in large measure just by statistics, even if there's no physical forces involved. We saw last time that the statistics are set up in such a way for a large number of particles that things will spread, and they'll spread irreversibly. Either energy or matter will spread irreversibly just because of statistics. And that's what's underneath all of thermodynamics. But now we need to learn the actual mathematics and details of thermodynamics. So the very first part of that is what I've called here under number 1, describing the situation. And I don't say describing the system, because the system turns out to be a term that we'll define here. So the very most basic thing is that we need to say what we mean by the system. So there's a system and there's a surroundings, and between the two of those, that's everything. Whatever isn't part of the system here is the surroundings. But you're free to choose that system and define it however you like. Usually, in most cases, it doesn't have to be the case. Usually there's some kind of walls that divide the rest of the world from your system. But you're free to choose that however you like, and you do it by convenience and by what your particular problem or interest happens to need for that case. If there are walls, sometimes the walls are purely imaginary, and that can work too. There are ways to treat a thermodynamic system even if it doesn't have anything around it at all besides what you draw, lines you draw with your imagination. But if there is a physical wall, then there are several different types that are common anyway. I mean, there's a zillion types in principle, but common types. Perhaps the most important is a set of isolating walls. These don't often really exist in reality, but they are imagining a system surrounded by walls that cuts it off from the whole rest of everything, so that what's inside is independent and untouched by everything that's outside. Those are called isolating walls. Isolating walls are isochoric. That means the volume can't change. They're impermeable, which means, because if the volume can change, then you can do PV work. So a volume change would allow the outside world to interact with what's inside, and they wouldn't be isolating walls anymore. The walls have to be impermeable. That is, you can't have matter flowing from inside the system to outside the system either. And they have to be insulating. You can't have heat flowing inside and outside the system. If the walls surrounding your system have all those properties, then what follows naturally is that there are some variables that you can talk about that describe what's going on inside that system, and those variables are held constant by the presence of the walls. So the fact that they're impermeable means that the number of moles can't change between the system and the surroundings, right? Moles can't be created and destroyed, and so we're going to assume anyway. I guess if you're considering nuclear reactions, they can, but we're going to ignore that possibility for now. So they can't change if stuff can't flow across the walls. Likewise, if it's isochoric, then that by definition means the volume can't change. And if none of that can happen, then the total energy inside the system also can't change. And so N and V and U are natural variables for this kind of problem. And we'll see other kinds of problems which have different sets of natural variables, but for an isolated case, these three guys are the natural variables. There's something else that I'll talk more about later when we get there, a little further down, but all three of these variables have a common property. It isn't obvious at first, but they're all what's called extensive variables. And what that means is they describe some quantity of something. They're not a force, they're not a concentration, which is kind of a ratio. They describe something that can be called stuff. Some stuff that exists. So mole numbers obviously are stuff. volume is space stuff. It's a region of space, and energy is energy stuff, if you like. And what an isolating system does, of course, is keep all this stuff inside. And so all these variables describing basically all the stuff that's conserved in an isolated system are extensive variables. Again, we'll talk more about that later. I say here that walls like this are very artificial, but very important, and that's because, as we'll see, isolated systems are particularly easy to deal with, and that makes it possible to formulate the laws of thermodynamics in the clearest way possible. It's not the way that's most useful. When you go out to actually do something useful in the real world, you got to have a more complicated system, but it's a good way to get the principles straight, so it's very important for that reason. Next is diathermal walls. These are walls that are still isochoric, volume can't change, and still impermeable, no mole flows, but they're not insulating, so heat can flow in and out. And now that means that there's some interaction between the system and the surroundings. It's kind of a weak interaction. It's just a loss or gain of heat from the system to the surroundings, but it is still a type of interaction. The surroundings can now affect what's going on inside the system. And that means that in this case, the variables that are sort of natural are the mole numbers and the volume, but the energy can change now. Heat is a form of energy, so the energy is not fixed anymore. Let me say that later on we'll talk about the fact that out here in the surroundings, there's often, the surroundings act as a temperature bath or an energy reservoir or a heat reservoir. And in that case, instead of the energy being locked or held constant by the walls, the temperature, a temperature bath has the property that no matter how much heat flows out, its temperature doesn't change. So that means the temperature is held constant. So every time we open the system by letting something flow in or out, in this case heat, there's usually something else that holds a different variable, a sort of complementary variable constant instead. In this case, it's temperature. Again, we'll talk more about that later. All right, so that's diathermal walls. Then there are variable volume walls. Now, for the first time, we're talking about cases where the volume can change. Still impermeable, but volume can change. And that can happen either with diathermal walls or with insulated walls. In either case, energy can flow even with the insulated walls right now, because when the volume can change, we can do PV work, which means the energy can change as a work transfer. If the walls are diathermal, then you can get heat flows as well, and the system can change energy by both work and heat. And finally, there are permeable walls too, or sometimes semi-permeable walls that allow some things to cross the boundaries, but not everything. Sometimes they're completely permeable to everything. And then that's a case where finally the mole numbers themselves can all change. But oftentimes out here there'll be a P bath, there'll be a T bath, or there'll be a chemical potential bath. And those things hold pressure, temperature, and chemical potential. We haven't talked about that much. Most people probably haven't seen the use of chemical potential much before, but we will talk a lot about it in this class. It's very important for chemistry. So those are the variables that are held constant. So this is the most open case, right? Everything's open now, but if we go back to the isolated case, then the natural variables were let me write them the other way, were volume and energy and mole numbers, and now they've been systematically replaced by pressure and temperature and chemical potential. And so you can see that when you open the system and allow one of these extensive quantities to flow in and out of the system, what tends to happen is that some intensive quantity like pressure or temperature or chemical potential just replaces the natural variables. All right. Next thing I want to talk about, I've made mention of this a bit already, of course, are surroundings. It's not just the walls that affect how the system behaves, it's also the surroundings. because there can be a temperature bath out here, right? So if I've got a system and if it's got diathermal walls, like, these thin walls indicate diathermal walls usually in my diagrams. And then what's out here is usually much bigger than the system itself. In principle, it's the whole rest of the universe, so in that case, it's always bigger than the system. But, the system really doesn't interact with the rest of the universe. It interacts with whatever is nearby. And that nearby stuff doesn't have to be much bigger than the system, but it usually is. And in that case, if it's big like that, then no matter how much heat flows out or how much heat flows in, when heat flows like that, of course, when heat flows out, you're taking energy out of the system and adding it to the surroundings out here. And if the surroundings weren't huge, if they were kind of the same size as the system or similar in size, then that would cause a temperature rise out in the surroundings. But if they're huge, they're too big to be affected by any small amounts of energy that flow out, and so there's no temperature rise. And in that case, they act as a tea bath. And that means that, yes, one of the natural variables is now in the presence of a temperature bath, or a heat reservoir, as it's sometimes called. Then temperature becomes one of the natural variables. There's also a volume reservoir, which also is called a P bath, and that is the same thing but for volume or pressure as for energy or heat and temperature in the other case. So in this case, you've got a big surroundings. Its total volume is much bigger than any volumes in here in the system. So if the system, for example, increases its volume at the expense of the surroundings, that doesn't change the pressure. If the surroundings are all of the laboratory in which you have your beaker here, or all of Albuquerque for that matter, or all of the world, then, moving the beaker, the plunger in the beaker up and down a little bit doesn't change the pressure of the surroundings, and so you have a P bath, or a volume reservoir, and that holds pressure constant. Pressure becomes a natural variable in that case. And finally, there can be a chemical reservoir, which does the same thing for mole numbers for chemical species as a heat reservoir or a volume reservoir does for temperature and pressure. So in this case, let's suppose you've got a dialysis bag here. That's a common case where you've got a permeable wall surrounding a system. Inside there's some sodium plus ions and maybe a bunch of other stuff. And the sodium ions, usually these dialysis bags are basically just filters. They have very tiny pores. Little things can get through the pores, like water molecules or sodium ions. Big things like proteins can't get through the pores, and so they're semi-permeable. Little things get through, big things don't. So that's how these kind of things work physically, but what that means is that the sodium can go in and out. Well, what then happens if this is in some giant beaker? So here's your dialysis bag here, inside a giant beaker full of some kind of salt solution. That's at, let's say, 0.1 molar. Okay, a little bit of salt coming in or a little bit of salt going out of your dialysis bag is not going to change. Well, it's not even going to change the concentration, but it especially won't change the chemical potential for sodium plus outside in the environment. And that means that this outside stuff here acts as a chemical reservoir, or a chemical potential bath is another name for it. So those are three different kinds of baths. You can have combinations of them, of course. You can have temperature, pressure, both baths. You can have temperature and chemical potential, but not pressure, and so on. There's all different combinations of different kinds of baths that you can possibly have. All right, that's sort of the most basic stuff. The next thing I want to do now is talk about is sort of put out this, it's traditional to describe thermodynamics or to set up thermodynamics in terms of laws of thermodynamics. So first law, second law, third law, usually just three laws. I've written what I've called here the extended first law. That means I'm putting more into this statement of the first law than people often do. Very often, statements of the first law are pretty terse. One sentence, and even a short sentence at that. I'm making it quite a bit longer here because I want to put some stuff in. And when we read through this, you won't understand it probably. I wouldn't understand it if I were you. So we'll go through it slowly afterwards. We'll go through it point by point, and so we'll lay out the statement, this law governs much of what isn't by itself, doesn't by itself govern what goes on in thermodynamics, but it governs a fair amount of it. We'll lay it out, and then we'll describe it bit by bit. So it says, there exist particular states of matter called equilibrium states, that's important, that are completely characterized, that phrase is also important, by 2 plus k variables. What does that mean? Well, for uniform systems, that is, if you don't have a lot of different kinds of patches and stuff, if you don't have a patchwork system, if its chemical composition is uniform throughout, then for an isolated system, there can be energy, volume, and now, before I've just talked about one mole number, but you can have as many mole numbers as you like, let's say k of them. If your system has k chemical components, then there will be k mole numbers associated with those. And that's the 2 plus k business, energy, volume, and k mole numbers. If you've got a tea bath, then temperature and volume and k mole numbers. If you've got a pressure bath, but it's insulated, then entropy, it turns out, pressure in k mole numbers. If you've got both temperature and pressure baths, then T, and k mole numbers, and so on. And so you can see in every case there's the 2 variables in this sort of first 2 spots here, slots, and then there's however many chemical components you have, and that's the k. In the simplest cases, k is 1, right? You got to at least have 1 chemical component, even if it's just a box full of water, then there's still 1 chemical component. So it's always 3 or more. And how many more depends on how chemically complicated your system is. All right, so that's the first part of the extended second law. Whoops. Extended first law, sorry. Second part is the energy of an isolated system, so isolating walls like we talked about above, is conserved. Energy is generally conserved, right? For open systems, so not isolated anymore, the energy can change, but in only one or both of 2 ways, heat and work. So there's only two ways by which the energy of an open system can change. And that means the energy change for the system. So whenever I write U here, that's the symbol for energy in this class, for thermodynamic energy in this class. The change in the thermodynamic energy of the system is equal to the change caused by a heat flow and the change caused by whatever work has been done. If it's a very small change, then du is equal to the small heat flow plus the small work that was done. All right, that's the statement of the extended first law. That's up on in the Learn site, just because I think this is an important statement. Learn. I think I'll write I don't think I have a second law statement on the Learn site, but I think I will put that up eventually. Let's go through it now. So it says here, this requires a lot of explanation. That is absolutely true. So let's go through it. The first thing is, up here, it says that all this stuff is only true for equilibrium states. All this stuff about 2 plus k variables, so 3 or more variables, that's only true for equilibrium states. An equilibrium state is a particularly simple state of matter. And it's the state you get if you just wait long enough without intervening or doing anything from outside. So you take a glass of water, seal it all off so that nothing can flow in or out, not heat, not matter, and there's no volume changes. Let it sit, and well, we know what will happen in the course of it, at most a few seconds really, or at most a few minutes. It'll settle down and stop moving. And if you wait maybe even 10 minutes just to be sure, then it will settle down completely, and that's an equilibrium state. Now let me say something, that I just said that glass of water is an equilibrium state, but is it really? I mean, what's going on inside that glass of water can involve a bunch of very slow, small processes, like, for example, radioactive decay. There's a certain number of oxygen atoms in that glass of water that have unstable nuclei that are not the stable isotope of oxygen. And they will be slowly decaying. Even the unstable isotopes of oxygen are very long-lived, so it'll take millennia for all those nuclei to eventually decay. I have read, I don't know if it's really true or not, that protons themselves, the things that are fundamental constituents of nuclei, are also unstable, but on a trillion-year time scale. So those are also slowly decaying to other things. And you can say then, strictly speaking, the system's not at equilibrium, right? Stuff's still changing. Stuff is slowly decaying, and it's not, strictly speaking, at equilibrium. Also, if I take something like a glass of water, but I don't seal it off real carefully, I just leave it sitting on the desktop, then the water is slowly evaporating into the atmosphere maybe, and oxygen is slowly dissolving, and CO2 is slowly dissolving. And so it's not really at equilibrium even with respect to chemistry in cases like that. But it's close enough, right? For most of our purposes, those kind of slow, small processes just don't count. So when we talk about equilibrium states, I'll try to be a little careful about what I really mean by equilibrium, but most of the time we're going to ignore minor, small processes like that. Strictly speaking, an equilibrium state doesn't involve any change with time. Also, no flows of any kind. And the fact that there are no flows, I'll illustrate, that means we have to distinguish between an equilibrium state and something called a steady state. So to distinguish between those two, let's consider our glass of water down here. That's an equilibrium state, at least if we ignore, interactions with the atmosphere out here. But let's suppose I put that same glass of water now on a warmer pad. So it's 100 degrees down here, and it's 25 degrees up here. Then what will happen if we sit and watch it for half an hour, let's say, is that heat will flow from the warmer pad up to everything else. But over time, and at first, the heat flows, heat will come up from the bottom, and we'll see the temperature rising up at the top of the glass. So things will be changing with time. But if I wait long enough, stuff stops changing with time, right? A temperature gradient will get established. It'll be hot down here, it'll be cooler up at the top, but it won't be changing over time. So you might be confused into thinking that that's an equilibrium state because there's no changes with time. But there will always be a heat flow in that case. Energy is coming from the warmer, and it's going through the glass of water, and it's ending up out here in the atmosphere. There's always a flow of energy. And that flow tells you that it's not really an equilibrium state, even though there's no change with time. That's a steady state, not an equilibrium state. Here's an even simpler case. I just take the glass of water and I put it on some kind of platform down here that a vortexer, I don't know if you guys know what a vortexer is, but it's a common benchtop instrument that causes this guy shakes the glass and causes a steady current to flow in the glass, a swirl to occur in the glass. If I do that carefully enough, this swirl doesn't change with time. It can also set up, and after pretty short period of time, it'll set up in a steady swirl. But there's obviously now a flow of matter in this case, a flow of water, and so it's obviously not an equilibrium state. All right, the important thing about equilibrium states for our purposes, for the first whole part of this class, is that thermodynamics deals only with equilibrium states. It doesn't deal with steady states of any kind, doesn't deal with situations where there's a heat flow, doesn't deal with situations where there's a matter flow, a fluid flow of some kind, doesn't deal with any kind of flow. So a chemical reaction, for example, that's ongoing, that hasn't reached equilibrium yet, even if it's ongoing at a steady pace, is not something that we can deal with in this first thermodynamics part of the class. Anything that's got a flow of matter, so in the case of a chemical reaction, the flow would be something like A plus B goes to C, right? The flow is from the products to the reactants to the products. Even if that's steady, that's a flow. And so not equilibrium. Only when everything is settled down and in fact the flow in one direction is matched by a backflow in the other direction, then you've reached equilibrium. Because then the concentrations of all these guys will settle down and not change anymore, and there won't be any flows. In that case, we're dealing with equilibrium, and thermodynamics only deals with those kinds of states. The fact that thermodynamics deals only with equilibrium states is a huge simplification. It's why thermodynamics is so powerful. Very often, physical theories like thermodynamics will be deliberately more simple than reality around us. I mean, there are very few true equilibrium states out there, and yet thermodynamics is extremely powerful because everything is kind of close to equilibrium most of the time, which means that even when thermodynamics doesn't strictly hold, it holds pretty well. And you can go a long ways with something fairly simple without the complications that come, huge complications that come when you're not at equilibrium. All right, next phrase, going back up here, completely characterized is the next phrase in our extended first law. That means that if we choose our 2 plus k variables, just 3 variables for the simplest cases, that we can predict all the other thermodynamic properties. Equilibrium states are especially simple. Only equilibrium states can be characterized by so few variables. Other things, well, here's the case, right? I'll come back to that point, actually. Other things require a lot more variables. We'll talk about that down here a little bit. But here's 3 cases. An isolated system, first of all, we saw that the natural variables are energy, volume, and mole numbers. That's 3 variables. That's enough. Knowing the values of those 3 variables is enough so that we can predict all the other equilibrium properties, all the other thermodynamic properties for that system. If it's not isolated, but there's a temperature bath out there, diathermal walls with a temperature bath, then the natural variables are temperature, volume, and mole numbers. Again, just 3, right? Notice we haven't changed the number of variables. We've just changed which exact variables we consider to be important. And the truth is, you could use internal energy over here too. It'd just be less convenient. The fact that there's a temperature bath here means that temperature is held constant. That's a fact you ought to make use of in your calculations, right? Any time something's held constant, you ought to make use of that fact. And so T, V, and N are the natural variables. They're the most convenient variables, at least from almost all cases. And here's a case where now the volume can change too, and there are temperature and pressure baths both outside. And so T, P, and N, again, 3 variables, are the natural variables. Always 3 variables are enough. We can predict the thermodynamic properties, all the thermodynamic properties from those 3 variables alone. In contrast to that, let's consider how many variables it will take to describe even something as simple as a swirling glass of water. We've seen that that's a steady state, but not an equilibrium state, therefore not covered by thermodynamics. In fact, covered by fluid mechanics, which involves solving a bunch of differential equations for full-scale functions instead of 3 numbers like this. I don't know if any of you have been exposed to fluid mechanics before, but it's a much more complicated theory. And the reason it's much more complicated is precisely because it's dealing with non-equilibrium states. Its whole purpose is to start trying to deal with non-equilibrium states, and immediately the difficulty grows hugely. In this case, if we want to know the state of this non-equilibrium swirling glass of water, what do we need to know? Well, we need to know how fast the water is moving at every point in space. We need a little velocity vector. We need to specify that velocity vector at every point in space. We need to probably specify the density at every point in space, too. And since there's basically an infinite number of points in space, or some very large number, even if we're going to coarse-grain the problem a little bit, there's a huge number of variables, in principle an infinite number of variables that are now needed to describe even this very simple non-equilibrium situation. And so jumping from equilibrium to non-equilibrium cases is always a big jump. A lot of extra work for non-equilibrium stuff. Now, we're going to talk about chemical kinetics at the end of this class. That's a non-equilibrium theory, which is more complicated, in fact, than thermodynamics in a lot of ways, but there's not so many variables in that case. It's not as bad as this case, and so we won't have to solve we won't have to solve too many differential equations, even in the chemical kinetics section. All right, completely characterized means if I know the values of my 2 plus k variables, T, P, and N, say, I can predict all the other properties. Here's an example of what that means. For an ideal gas, ideal gases are always the example everybody chooses at first because they're the simplest case. One chemical component, let's say oxygen, pure oxygen. So K is equal to 1, 3 variables are enough. In that case, suppose I want to know the pressure. Well, we have the ideal gas law, right, which says that pressure is equal to nRT over V. There are 3 variables in that expression, right? R is just a constant, that's the gas constant. So T, V, and N, knowing those 3 variables are enough for us to predict the value of pressure. And as I change the values of these variables, the pressure changes, and I can predict at every point and for every set of conditions what that pressure will be. And here I do the calculation. I won't go through that because I think everybody knows how to do those kinds of things. The ideal gas law is something I'm sure everybody has seen plenty of already in their time here at UNM. Here's another case. In this case, it's the internal energy so a different property, different thermodynamic property for an ideal gas. That turns out to be, for a monatomic ideal gas anyway, that turns out to be 3/2 nRT. It only depends on 2 variables, that's fine. That means it doesn't really depend on the volume in this case, but that's fine. The volume is still sort of formally there. We count it as still one of the basic variables. It's just that in this particular case, there's no dependence on it. So T and N are enough, and you can do the calculation. And again, as T and N change and the energy changes, we can predict and calculate in every case. Here's another property, the enthalpy. That's 5/2 nRT. Same story, just a different formula. Here's the entropy in this case. We talked about entropy last couple of lectures. We have a feeling for what that is, but there's a thermodynamic way of thinking about it. We'll talk about entropy a lot in coming days. Here's the expression for the entropy for an ideal gas. And let's look. There's mole numbers, there's mole numbers, there's mole numbers, there's volume, there's mole numbers, there's temperature. There's lots of little places where all those variables occur, but there's only 3 variables. If I know those 3 values, I can predict the entropy for every set of possible conditions. And likewise, the chemical potential, we haven't talked about that much yet, but here's another expression for that. All these things are called equations of state. We'll come back to that. All these relationships are equations of state. And again, temperature, volume and mole numbers, 3 variables. Isothermal compressibility, now we're getting into more unusual properties. That's V over nRT, depends on V, N, and T. The thermal expansion coefficient, that's how much the gas expands when you change the temperature. It's just 1 over T, and so on, so on, and so on. Every single thermodynamic property can be predicted from just 3 numbers. The 3 numbers correspond to a thermodynamic state of the system. The state of a system in any branch of physics or physical chemistry, like electrodynamics or quantum mechanics or classical mechanics or fluid mechanics or thermodynamics, any of these things, they all have a state. That's the amount of information you need in order to predict all the properties. And for thermodynamics, it's just 3 numbers. The state for a thermodynamic system is especially simple. All right. Now I want to talk a little bit about, well, actually let me stop there. I think we've gone on long enough. I don't want this video to get too long, so I'm going to stop and I'll pick up the next topic next time.